We do both.
We can do whatever you guys want. What's that? I can give you whatever. All right, Pythagorean theorem first. Let's suppose we have 2 trains leaving the station, one heading east, let's say at 50 miles per hour, and one heading north at, let's go 80 miles per hour. High-speed train for the United States here. In China, they go about 300 miles per hour.
Yeah, they're really fast.
Yeah.
But
Didn't they just make another one that goes like twice that fast?
Not twice, I don't think.
What do they?
But they have high-speed trains.
They use they don't use track. They use
Magnets.
like cold.
Yeah, I
something
think so.
Cold, I think. Yeah, magnets and like cold air or something like that. No?
Yeah, something to get a separation. There's not, like the friction is
They
decreased.
Use what roller coasters use.
What's that?
They use what roller coasters use magnets.
Roller coasters use magnets?
And your
A lot of
ones
them
too.
Serious? Wow, I'm not going on
They
anything.
just use
Forget
that
it.
technology on the train.
What happens? You know, the magnets. I don't like that idea. All right, but anyhow,
Once unstuck, like if it unsticks, then you die.
I
No,
know.
it still
No, it's
wraps
a-
around it, so it doesn't, like, even if the magnets stop working, like, you would still be attached.
Oh yeah, the magnets.
Wait, okay, you're going 100 miles an hour down, the magnets stop,
The
they
magnet
stop.
keeps it
You're going to go, I don't care if you're held in by a.
It's still
No,
wrapped
it's
around
wrapped
it, so
around.
it's still basically latched in there. The magnets just keep it from
Okay,
touching. So they
that's
don't
the
break.
car. The car is attached to the track. I'm talking about my body being launched because I go through the seatbelt because it stops at 100 miles an hour. That's what I'm talking about.
No, I think we did. What is it called? We did liquid nitrogen back in high school, and we used a magnet, and the magnet I think it was floating.
Oh, yeah, there's some cool things you can do with that
And,
stuff. I
think
agree.
I think that's what he said they use in China for the
Wow,
tracks. So there's
maybe.
no friction.
Wow. All right, here we go. You got, they leave at the same time, one's 50 miles an hour, another's 80. The question is, how far apart after 1 hour? This is not even going to come out nice.
So what did you just do? A squared plus B squared equals
Yeah,
C squared?
exactly right.
And then just solve for C.
Yep. And then how fast is the distance between them changing?
That would be derivative.
Yes, distance changing after 1 hour. That's a typical kind of question you're going to get. So what do? You say x squared plus y squared is equal to z squared. The first question is, just what Danny just said, use Pythagorean theorem. 50 squared plus 80 squared is z squared. 2,500 plus 6,400 is z squared. Z is going to the square root of 8,900, which is 10 square roots of 89. Nice answer. Okay, that's what z is in 1 hour. Now, how fast is the distance between them changing in 1 hour? That's where you need a derivative. So take the derivative with respect to time. 2x dx dt, 2y dy dt, 2z dz dt. 2's will cancel.
We're just plugging everything in.
Plug everything in. So x is equal to, in 1 hour, x is 50, dx dt is 50. Y, 80, dy dt is 80. Z, 10 square roots of 89. dz dt is what we're looking for. That's how fast the distance between them is changing.
Well, how do we know what dx dt is?
That's given to you. That's 50 miles per hour. That's how fast x is changing.
It's position over time.
So, dz dt is equal to 2,500 plus 6,400 divided by 10 times the square root of 89. So, this gives you 8,900 over 10 square roots of 89. I would probably leave the answer, well, no, I wouldn't. 10 cancels out this.
Multiply by 89.
You should multiply by the square root of 89. You get 890 square roots of 89 over 89, so you end up with 10 square roots of 89. These problems are so cool. So not only is it's amazing. Not only is the distance equal to 10 square roots of 89, but the distance is changing at a rate of 10 square roots of 89. As a matter of fact, if I ask you how fast the distance between them is changing after 2 hours, it would still be 10 times the square root of 89. It's cool stuff. It's just, I tell you, math is just awesome. That's all there is to it. All right, but anyhow, that's one kind of problem I would give you. I would give you possibly another kind of problem. The other kind of problem is hot air balloon kind of problem, okay? Here's a hot air balloon in the shape of a sphere. Here, you guys do this one. You guys do something here, okay? You guys do this. You got a hot air balloon, and let's suppose that the volume is increasing at a rate of 200 cubic meters per second. Okay? So you got this torch thing, this heat source. The balloon is expanding at a rate of 200 cubic feet per second. How fast is the radius increasing when, go ahead, what's that?
Remember it's asking how fast something is increasing, would that be the derivative?
Yes, with respect to time.
It's half pi r cubed, right?
The volume of this thing is 4/3 pi r cubed.
Oh, 4/3?
Yes.
Which one did I do?
What did you say, 1/2?
Oh, it's not 1/2.
None of them are 1/2.
Yeah.
Yeah.
4/3 pi r cubed, right?
Yes. How fast is the radius increasing when the radius is equal to, let's say, 10 meters? Go ahead, you guys do one.
Can you say what the formula is?
Yeah, the volume is 4/3 pi r cubed. Do, 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 do. And that'll be your test. And on Thursday, I'm going to pass out this sample final. You're going to do it. I will correct it. If you do well enough, you can be done Thursday. I'm hoping next Monday we have nobody left because everybody just does so well on the thing Thursday. That's what I'm hoping for.
We're looking for DRDT.
You are looking for, yes, you are, DRDT.
That was a good story.
See, how can you guys, I don't understand how people can do that. You can actually understand what they said going by out there like that?
No, she said me.
She said something
girl
about
stuff,
bathroom.
like-
but-
I can never understand those kinds of conversations, but there are people that can. I don't know how they do it.
It's an art.
I guess. My wife can do that all the time. She can be talking to me, of course, when she talks to me, she uses up 1/3 of her brain. So the rest of her brain can be used for anything she wishes. So I guess she can understand several conversations at once when she's talking to me.
The 200 will be on the other side, correct? On one side.
It's on one side, that's true.
And the other stuff would be on the other.
And the other stuff is on the other side. That is true too. So count 2 in the spring.
Yeah.
Yeah, good deal.
Think you'll have like 30 and then 5.
What?
Think you'll have like an increase and then a decrease, just like this happened?
Oh, like for this
Yeah,
class?
we had a
We had a lot of people and then they.
We had,
This is too hard.
how many did we start with?
I think we actually have the same amount.
14.
No.
We didn't start with that many more. I lost maybe a couple. 14?
Something like that.
And what do we end up with? Well, Chris is still alive, believe it or not. He's not here tonight. 2, 4, 6, 8, 10, 11, 12. We lost a couple along the way.
I don't think
There was,
There was that guy with glasses right there,
there was a,
and then I don't remember who else was here.
yeah. There was somebody else back there, wasn't there? Was there somebody else back there with you? No? Nick? Oh, yeah, Nick was back there, and then Nick floats around, that's true.
He just floats around.
I'm a floater.
But Danny's been consistent. Huh? Melissa's been consistent.
Yeah, this is the rest of, yeah.
Carolina's been consistent. Damien's been. Trent has. Duong has been. Gester floated a little bit. He was there, and then he kind of went to there.
What'd you get?
Jeff's right there. Solid. You're solid as a rock, Jeff.
Six top?
Yeah.
What'd you get?
I got one half, one divided by two.
1 divided by 2.
V doesn't disappear anywhere, does it?
What's that?
V doesn't disappear anywhere. It's V, dV, dt. That means we would have to find the volume of the initial.
No. What are you talking about? V is gone. What do you got? You still got V here? There's no V there.
Can we go over it?
Yeah. Yeah, let's go over it.
Let's do this.
Let's do this. What do we have to do? We have to take the derivative with respect to time. It's a related rate problem. So dv dt. 3 comes out, knocks out this 3. You get 4 pi r squared dr dt. Now, 4 pi r squared. What is 4 pi r squared? That, believe it or not, is the surface area of a sphere. It's 4 pi r squared. Think about it. You've got a sphere that's expanding. How fast is that volume changing? It's changing at a rate that's equal to what the surface area is times the rate of change of the radius. That makes some sense because it's expanding out with the surface area times how fast the radius is changing. If you think about it, that should make some sense. Hopefully it makes some sense. Anyhow, dv dt is what we know. That's 200. Now, let's keep track of the units. That's cubic meters per second. That's equal to 4 pi r squared. That's 10 meters squared. Okay? 10 squared, 10 meters squared, which is 10 squared times meters squared, times, yeah, it's 100. dr dt is what we're looking for. So what do we have? We have 200 cubic meters per second. Okay? Now we have 100 times 4 pi, so that's 400 pi. Now what do we have? We have meters squared, that's dr dt. So we cancel this, we get 1 over, Danny, just what Danny had. 1 over 2 pi, pi's down here. We have cubic meters over meters squared, that's meters per second, and that's dr dt. And that's exactly what you would expect the units to be for a rate of change of a radius in meters per second. And it's 1 over 2 pi.
We don't care about units, so it's.
No, I'm not even going to carry out. I probably don't even, I may or may not have units on the thing. But I'm not going to, you're not going to get something wrong because of the units, because all the units will be the same for every one of the answers, okay?
Are we done?
Yes, we are.
Let me take a picture.
Thank you.
Okay. There's all the stuff. You took a picture of some of the stuff already.
Yeah, the test.
The test itself. Okay. Here, let me get out of your way.
Time, same place.
What is this? Oh.
Let us